confinement nuclear fusion. All right. Is my presentation coming through okay?
Yes, it's all perfect. Please continue.
Okay, great. All right. So one of the things, I'm sure you're all familiar. Every morning when you get up, you see the sunrise, and that's a great example of gravitational confinement. What I'll be talking about is inertial confinement. Instead of having gravity pull in the atomic nuclei to fuse them, we're dealing with inertia. This was demonstrated first in the 1930s using particle accelerators to slam deuterium ions together. After the Manhattan Project, William Teller led a group to use fission explosions to do inertial confinement. And then there's been about 20 or 30 groups that are using plasmas and lasers to do that. Most recently, Lawrence Livermore Lab has set some records using the laser method to confine the deuterium or tritium together. And at the heart of that is micro and nanotechnology, and that's what I'm going to be talking about. So the Lawrence Livermore National Lab, their inertial confinement system uses 192 lasers, high-powered lasers. It's focused on one central piece of material in a vacuum chamber. When it hits the holder, it generates X-rays. This inertially accelerates the deuterium and tritium together, which fuses them, producing energy, helium, and neutrons. So that's the essence of inertial confinement via lasers. And there's been two instances at the end of last year and in July of this year repeated where they got a net positive gain of energy out of the vacuum chamber. So that was the headlines. For those of you who've seen, there's been a lot of videos, a lot of papers on this. These are just some photographs that I've captured from them. On the top left is the tiny diamond shell that's used to contain the fuel, the deuterium fuel. It starts as a silicon sphere. And that's where the silicon micromachining and nanotechnology comes into play. The shell actually uses microfluidics to both evacuate the silicon from the shell and to attach a tiny tube to fill it with fuel. It's then put in a structure called the hull room, which holds the fuel pellet, which is then put in the vacuum chamber where it is hit by the lasers. So a really interesting, intricate system to generate nuclear fusion. It's not the tokamak approach that we're so familiar with over the last couple of decades. So the fuel pellet holder, the hull room. This is a copper gold structure. On the left, it's the before picture. On the right is the after picture. But on the left, you have the fuel cell pellet, or the fuel pellet in the center. That's the diamond sphere filled with the heavy water ice. When it's hit by the lasers, X-rays are generated by the metallic holder, which inertially confines the material, pushes it together, and initiates fusion. So that's the basics of what's going on. On the right, you can see the results of the laser bombardment and nuclear explosion, micro explosion, with this small metallic pellet. So one of the key processes in this is silicon micro or nano machining. We often refer to it as MEMS or NIMS, micro or nano electromechanical systems. This is the industry I've worked in for several decades. And it's a subset of semiconductors. You typically use silicon, but you might also use glass or silicon carbide or gallium nitride. The chips are three-dimensional. They're not just electronic, but they actually have moving parts. They're found in smartphones, automobiles, smartwatches, your inertial sensors, your microphones, RF filters. Those are all micromachine devices. And these are some SEMs that show you all the interesting three-dimensional structures that can be etched into these. This micromachining technology is kind of the core of the fuel pellet. So just a quick review, how is silicon micromachining done? How is the silicon sphere made? And it starts the same way you make a chip. We use silicon dioxide sand. You separate the purified silicon. You grow a single crystal ingot. You slice that into wafers. And then you do some polishing. So just like we make silicon wafers, you're leveraging these same techniques to make the silicon fuel pellet mandrel. And so you're almost making a silicon ball bearing. So I like to throw this in there. So in addition to leveraging silicon micromachining, we're leveraging over a couple of centuries of making silicon or of making steel ball bearings. We make about 3 billion of those a year. So we obviously know how to make very shiny round spheres. And so you basically cross the silicon fabrication techniques with some of the techniques that have been developed over the centuries. So we're leveraging all this ancient, almost ancient technology to make something really cutting edge for fusion. The process that we highly rely on to make these extremely smooth surfaces, it's less than 10 nanometers of surface roughness on these spheres, just like a silicon wafer. That's probably one of the smoothest surfaces that can be man-made, fabricated by man. We're taking the techniques for chemical mechanical polishing, where you have an abrasive and a chemical reaction that smooths off the surface of the structure. On the left, we're showing how it's done for flat wafers. On the right is a diagram of how it's done for these silicon spheres. So you have a polishing pad, but the spheres are sitting in grooves on the bottom. And so you get this counter rotation, you have the spheres rotating, and you gradually, with this colloidal slurry, this chemically reactive slurry, you chemically and mechanically etch away all the surface abrasion and scratches and roughness on those surfaces. You got to get down to less than 10 nanometers of smoothness. And the reason, okay, and this shows you the total fabrication. So the total fabrication flow, you've got to get the interior of that diamond sphere extremely smooth, so you have a uniform compression of the fuel. So again, this shows you cutting thick wafers, dicing the wafers. So instead of having chips for an integrated circuit, you've got cubes for a sphere. You then knock off the corners, round that with that abrasive process. You use CVD coating to put on the shell. You've got an etch a very high aspect ratio channel, a single channel into that diamond shell, and then remove the silicon. So that's a microfluidic feat there, because that's a lot of material. You've got to attach that tube, and that's kind of shown there in the picture. That's done manually now, so it's a very labor-intensive process. And then you've got to fill this with heavy water in the form of an ice. So it's an ice deuterium tritium mixture that's in the combustion chamber. And here's some references down below if you want to dig into this. This has been published since 2009 to kind of step you through what's been done to make these pellets, and they gradually shrunk the pellet size. So the chemical vapor deposition process is typically plasma or microwave enhanced. This again is a modified tool leveraging machine tool coating, diamond semiconductor power IC processing, and the graphene memory processes that were developed about a decade ago. So we're taking the same tools. Instead of using a planetary rotation like we would on the right for a wafer, we're rotating the spheres in little tracks with the plasma, the methane hydrogen plasma above, which coats this with a dense carbon or diamond sphere. Okay, next comes the micromachining part. So you've got to both micromachine through that diamond shell, and then you've got to etch away the interior silicon. On the right is some old SEMs of some processes I developed years ago, where we do a high aspect ratio etching followed by an isotropic silicon etch in the underlying silicon structure. So it's kind of akin to that. They've looked at different wet etches. Silicon wet etches can be quite rapid. Of course, you have surface tension issues of getting that out of high aspect ratio channel. You have a variety of plasmas that have been used, SF6, CF4, xenon difluoride. So those are all techniques that have been developed and I could say perfected to get these shells to be formed, to remove all that, up to 1 millimeter or 2 millimeters thick silicon, which is a lot of silicon. So the question is, can we use laser-based inertial confinement as a path to carbon-free green energy? Or is fusion always 50 years away? Because that's my whole lifetime. When I was an undergrad, I thought about nuclear engineering. It's like, it's 50 years away. I'm not going to get into that. So the question is, can we do it? Do we have the technology? This is a daunting challenge. And this is kind of analogy I thought was interesting in that, they're essentially putting tiny carbon spheres into a laser furnace. And it's akin to what we first started off with coal firing, thousands of years ago. In China, Britain, and Greece, they independently discovered that you could burn coal and wood. LLNL is basically doing 2 good ignitions in 6 months. So essentially, and they produced heat. That's all they've done. So we're essentially at this wood fire stage where we're able to do it twice in 6 months. So we've got to get to the point where we're shoveling in coal, in like the steam loaded, the Industrial Revolution. We started using manual shoveling to generate steam. We started using it to turn a steam turbine. It was 1% efficient in the 1880s. We're up to 30 or 40% efficient. We're using conveyor belts, crushed coal, etc. But we need 900,000 ignitions a day to hook into the power grid. This almost seems impossible when you look at what they're doing now. And obviously things have to change. There was a big change from the campfire to the conveyor belt power plant. And these are the changes that have to be addressed by all the startups and the government labs that are working on this problem right now. And I ran across, I'm in semiconductors, and I ran across another interesting piece of technology that's being used at advanced node wafer fabs like TSMC, Samsung, Intel. To fabricate these 3 or 5 nanometer wide line widths for transistors on wafers, ASML has a EUV, extreme UV stepper system that relies on laser vaporization of tin droplets. This vaporization generates the 13.5 nanometer wavelength light source, and they're doing this with 50,000 tin beads per second shot into a vacuum chamber. So you see the analogy there between what they can do and what we need to do with the fusion project. So for the fusion project, we just need to do 11 shots per second. Of course, that's a daunting challenge, but there is a path forward. There has been an advanced group that does this. These steppers cost $130 to $400 million each, so they're expensive. But they're distributed across the world. The technology is there to indeed laser vaporize tiny pellets in a vacuum chamber. So I think it is possible. So barriers to overcome. The biggest barrier to overcome for fusion is to increase the gain even further. So the scientists at Lawrence Livermore say they've got to increase the gain by 100x. They're going to have to work on the lasers. They're going to have to work on the pellets. They also need to go into production. You've got to shrink and mass produce these fuel pellets. And, there's people thinking about, again, how to leverage semiconductor manufacturing, maybe change the materials, lower the cost. You can produce tens of thousands of chips on one silicon wafer. Can you do the same thing on a silicon wafer, produce tens of thousands of pellets? So that's one method or one path that we have to go down to. And then you've got the rapid loading system. And again, I think that's where ASML has kind of shown us the way to go. Now they're injecting liquid tin into the system, but perhaps that can be modified to inject a solid shelled fuel pellet into the system. You're going to have to address buildup in the combustion chamber, and that would attenuate the signal. So these are the kind of practical engineering things that have to be addressed. So it looks promising. We have made records. We have finally gotten over the barrier of more energy in than energy out. Of course, as everyone will point out, there's a lot more energy used to power those lasers than we get out of the chambers. But still, I think with gain increases, this can be overcome. If you'd like to learn more about this, I had an article on this published in CMM Magazine, the October issue. There's a lot of other references that are in the talk that'll be made available after this, and please contact me. You can also check out my YouTube channel, Micro to Nanotechnologies. We'll have a video on this as well, and other interesting micro machining and nanotechnology topics. So with that, I'll wrap it up and take questions. Thank you.